In the kidney, the loop of Henle is the portion of a nephron that leads from the proximal convoluted tubule to the distal convoluted tubule, named after its discoverer, the German anatomist Friedrich Gustav Jakob Henle. The loop of Henle's main function is to create a concentration gradient in the medulla of the kidney, by means of a countercurrent multiplier system, which utilizes electrolyte pumps. The loop of Henle creates an area of high urea concentration deep in the medulla, near the papillary duct in the collecting duct system. Water present in the filtrate in the papillary duct flows through aquaporin channels out of the duct, moving passively down its concentration gradient. This process reabsorbs water and creates a concentrated urine for excretion. Structure: the loop of Henle can be divided into 4 parts. Thin descending limb of loop of Henle. The thin descending limb has low permeability to ions and urea, while being highly permeable to water. The loop has a sharp bend in the renal medulla going from descending to ascending thin limb. Thin ascending limb of loop of Henle. The thin ascending limb is impermeable to water, but it is permeable to ions. Thick ascending limb of loop of Henle. Sodium, potassium and chloride ions are reabsorbed from the urine by secondary active transport by an RKCl cotransporter. The electrical and concentration gradient drives more reabsorption of Na+, as well as other cations such as magnesium and calcium. Cortical thick ascending limb. The cortical thick ascending limb drains urine into the distal convoluted tubule. The tissue type of the loop is simple squamous epithelium. The thick and thin terminology does not refer to the size of the lumen, but to the size of the epithelial. The loop is also sometimes called the nephron loop. Blood supply. The loop of Henle is supplied by blood in a series of straight capillaries descending from the cortical efferent arterioles. These capillaries also have a countercurrent multiplier mechanism that prevents washout of solutes from the medulla, thereby maintaining the medullary concentration. As water is osmotically driven from the descending limb into the interstitium, it readily enters the vasa recta. The low blood flow through the vasa recta allows time for osmotic equilibration, and can be altered by changing the resistance of the vessel's efferent arterioles. As well, blood in the vasa recta still has large proteins and ions which were not filtered through the glomerulus. This provides an oncotic pressure for ions to enter the vasa recta from the interstitium. The main function of the loop of Henle is to set up a concentration gradient. Physiology. The descending loop of Henle receives isotonic fluid from the proximal convoluted tubule. The fluid is isotonic because as ions are reabsorbed by the gradient time system, water is also reabsorbed, maintaining the osmolarity of the fluid in the PCT. Substances reabsorbed in the PCT include urea, water, potassium, sodium, chloride, glucose, amino acids, lactate, phosphate, and bicarbonate. Since water is also reabsorbed, the volume of fluid in the loop of Henle is less than the PCT, approximately 1/3 of the original volume. The interstitium of the kidney increases in osmolarity outside as the loop of Henle descends from 600 mosml in the outer medulla of the kidney to 1200 mosml in the inner medulla. The descending portion of the loop of Henle is extremely permeable to water and is less permeable to ions. Therefore, water is easily reabsorbed here and solutes are not readily reabsorbed. The 300 mosml fluid from the loop loses water to the higher concentration outside the loop and increases in tonicity until it reaches its maximum at the bottom of the loop. This area represents the highest concentration in the nephron, but the collecting duct can reach the same tonicity with maximum ADH effect. The ascending limb of the loop of Henle receives an even lower volume of fluid and has different characteristics compared to the descending limb. In the ascending portion, the loop becomes impermeable to water and the cells of the loop actively reabsorb solutes from the luminal fluid. Therefore, water is not reabsorbed, and ions are readily reabsorbed. As ions leave the lumen via the NaK2Cl symporter and the NaH antiporter, the concentration becomes more and more hypertonic until it reaches approximately 100 to 150 mOSml. The ascending limb is also called the diluting segment of the nephron because of its ability to dilute the fluid in the loop from 1200 mOSml to 100 mOSml. Flow of the fluid through the entire loop of Henle is considered slow. As flow increases, the ability of the loop to maintain its osmolar gradient is reduced. The vasa recta also have a slow flow as well. Increases in vasa recta flow wash away metabolites and cause the medulla to lose osmolarity as well. Increases in flow will disrupt the kidney's ability to form concentrated urine. Overall, the loop of Henle reabsorbs around 25% of filtered ions and 20% of the filtered water in a normal kidney. These ions are mostly Na+, Cl-, K+, California 2+, and HCO3-. The powering force is the NaK ATPase on the basolateral membrane, which maintains the ion concentrations inside the cells. On the luminal membrane, Na enters the cells passively, utilizing the NaK2Cl symporter. Then the NaK ATPase will pump 3 Na out into the peritubular fluid and 2K into the cell on the non-lumen side of the cell. This gives the lumen of the fluid in the loop a positive charge in comparison and creates a Na concentration gradient, which both push more Na into the cell via the NaH antiporter. The hydrogen ion for the antiporter comes from the enzyme carbonic anhydrase, which takes water and carbon dioxide and forms bicarbonate and hydrogen ion. The hydrogen ion is exchanged for the Na in the tubular fluid of the loop of Henle. History. The loop of Henle is named after its discoverer, German anatomist Friedrich Gustav Jakob Henle.